Hey Chem students, today we're going to talk about kinetic molecular theory or KMT. So the goal here is to be able to use the kinetic molecular theory to explain the properties of solids, liquids, and gases. Including in this is intermolecular forces, elastic collisions, kinetic energy and temperature, and some key terms intramolecular forces, not to be confused with uh, intermolecular forces, crystalline structures, and amorphous structures. Okay, so kinetic molecular theory explains why matter behaves the way it does. The major points. So there's a lot of space between the particles, and collisions result in no change in energy. This part is specifically about gases. Um, these three little annoying animations at the bottom that are just going to keep on playing for this whole slide are showing a solid on this left here, a liquid in the middle, representation obviously, and a gas on the right. And they're just going to keep playing over and over again. But as you can see, there's a lot more space between the gas molecules uh, than the liquid and the solid. And we'll talk about the no change in energy in a second here. There's no attraction or repulsion between gas particles, so they don't pull on each other. They don't have any charge where they're where they're pulling against each other or repelling each other, um, and so that doesn't matter at all. Um, the particles are in constant random motion. Now, that doesn't mean that they randomly change direction all over the place, but there should be a word in here saying linear, constant linear random motion. Uh, so they'll follow a line, a motion that they have until they bump into something else, whether it be the wall of a container or whether it be another gas particle. And we'll see a kind of a representation of that as we come up here. And then the speed that the particles move increases with increasing temperature. And I've already told you guys this, and I'm pretty sure you know this at this point. As soon as you add energy, you're adding energy to those molecules and they're moving faster. So your solids are moving very little because they are not as warm. Uh, there's not as much energy there for those molecules to move. Liquids moving more so there's a little more space. There's the ability for it to flow freely and fill that, take the shape of the container that it's in because that energy uh, is enough that those molecules can separate from each other, can break the forces between the molecules. Whereas gases even more so, and then they'll actually fill the container uh, whatever size it is. They'll just spread out to do that. All right, so the difference between intramolecular forces and intermolecular forces. So intra means within. So molecular forces that exist within molecules. So that means that these forces that are holding a molecule together is an intramolecular force. Ionic and covalent bonds involving electrons. So both ionic and covalent count in this category. So NaCl, the bonds that hold Na and Cl together, is an intramolecular force. The bonds that hold a water molecule together, H2O, that is an intramolecular force. Okay, so here's an example of water molecules, and so these bonds right here are the intramolecular forces holding it together. And then ionic, got the NaCl and no animation for some reason, but these bonds right in the middle here holding them together. The difference between that and intermolecular forces are that these are forces between molecules. So the intermolecular forces in these cases are these bonds. And you may want to draw an arrow to these things so that you know which is which. Um, one way to remember that is if you think of like an international airport, international airports fly to other countries. So the countries are like the molecules, and these are the connections between molecules. So like connections between countries on an airline. Now we don't really say intra for very many things at all. Um, the only thing I can think of as an example for this, and I even looked up words that start with intra. We just don't use it very often. We use inter for a lot of things, interconnected, uh, intermediate. There's all sorts of words that we use inter for, but intra, the only one I can think of or could find that most of you would know and um, be able to relate to was intravenous. So if you're getting like an IV, that's what it stands for in the hospital, giving you fluids or medication or whatever, that's intravenous, meaning it's within your venous system, your veins. So that's another way you can maybe remember that. Intravenous, international. If you just remember one, you can hopefully remember the other then. All right, so one of these rules is that as temperature increases, the speed of particles increases. So we know that that's why solids are at lower temperature for the same materials. Let's say water, right? Anything below 0 degrees is solid. Anything above between 0 and 100 is liquid, and 100 degrees and above turns into a gas. So as we decrease temperature, the speed decreases as well of these molecules. And therefore, the intermolecular forces, the IMFs, you'll see it as in some of these other ones, uh, are able to take hold and pull those molecules closer together. So this is kinetic energy, this motion. And if you're trying to remember this, I know you've been taught it in the past, and probably one of the examples you got was a bow and arrow. So um, there's potential energy and there's kinetic energy. Potential is, imagine you've got your bow and you pull the bowstring back, you've got that arrow in there. That's potential energy at that point. You've got that ready to release, and that energy is pent up at that point. Uh, becomes kinetic energy as soon as you release that bowstring, and that arrow is now in motion. And so the amount of kinetic energy it has is what it would put out on whatever target it hits. So something like a bullet has higher kinetic energy than an arrow because it moves so much faster. Um, so that's kinetic energy, energy of motion. And these particles, this increases with increasing temperature because these particles are moving faster, right? I mean, it's just logical. The faster something moves, the more kinetic energy it's going to have. All right, elastic collisions. So um, this is something that's kind of it's hard to even come up with an example of in what we can see, you know, larger than a molecular scale, because we have things like air friction and we have gravity and we don't have perfect systems. We're not in a vacuum. But what elastic collisions are basically is that when gas particles collide with the sides of a container and exert a force. Sorry, I guess I'll skip this part for a second right here. Um, oh man. Okay, I'm gonna come back to it because yeah, I was talking about this. I'll go back to this, I promise. Okay, so all collisions between particles and with their containers are elastic. So elastic means that there is no loss of energy in this case. Um, so if you imagine you had a bouncy ball, right, and you drop it, and every bounce it gets a little bit lower and lower, and then eventually it's dun, 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 and it eventually starts rolling, right? Well, with elastic collisions, that means that they bounce back to the exact same spot, exact same height. They never lose energy. The energy that uh, the speed that they hit the wall with, they will come off of the wall with, or the ground, or whatever. Um, and so if they hit another particle, they will impart that energy that onto that particle, and there would be no loss of energy at any point. So make sure you know that elastic collisions, it means that there's no loss of energy. Okay, now I'll go back. Sorry, guys. So when these gas particles collide with the sides of a container, they exert a force, and this force is called gas pressure. So you can kind of picture these gas particles flying around a container. Um, and this is kind of amazing, actually, when you think about it. And you would never, like, we all know that we can have gas pressure. Uh, one of the like, here's the one of my pet peeves. Um, condiment containers like ketchup containers. Ketchup's the classic one. So you got a ketchup bottle, right? And you know the ones that are upside down, like they sit on their lid normally. That's where they're supposed to stand so that you can just open the lid and then you can squeeze out a bit of ketchup and then close the lid and you don't have to like, shake the bottle so that they come near the spout. Uh, Sounds great in theory, except you you store your ketchup in the fridge, keeps it nice and cold, and this is where kinetic molecular theory comes in. The gas particles that are in there in the air part of that container, the part that's not the ketchup. Those gas particles, when it's in the fridge, they're moving nice and slow. They're not putting out much pressure on the walls of that container. Uh, and it's had time to like it's not a perfect sealed container, so it has time to like, equal out in the fridge. You pull that out, you put it on your table, and you're, making your meal. You're all there. You're ready to put it on your burger or hot dog or whatever, and you open up that lid, and automatically the ketchup just starts spurting out. Sometimes it gets all over the lid, it gets on your hand. Uh, you get like 3 times more than you actually want on your burger. That's because those molecules, those air molecules, these ones right here have more energy because they heated up over time, just from being outside of the fridge. So now they have more energy and they're bouncing against the walls of that container and putting out more gas pressure. So they're pushing against that container, and because it's ketchup on the bottom, it has nowhere else to go but to push that ketchup down. So it pushes the ketchup down, pushes it out of the spout, and gives you like 3 times more ketchup than you actually wanted on your hot dog. And you're like, ah, man, come on, like this is ridiculous. Uh, so I hate those containers for that reason, and I refuse to buy them. I don't, and if I do, like I will keep them upside down, quote unquote, meaning the spout is up so that um, I can let the gas escape first. And when I open the lid, and then I can, turn it upside down and shake it and get the ketchup out. So that's my example of gas pressure and how it increases. It increases when you increase temperature, and it decreases when you decrease temperature. Another thing you probably have done actually is take a milk bottle, right? Um, Milk jug, and you rinse it out hopefully, after emptying it, because I think you need to recycle it now. So you rinse it out with hot water and you empty it out, and then you put the lid back on. And if you leave that for a minute or so, that bottle is going to expand. Even if you just leave your milk jug out actually and just leave it sealed, you'll see that over time as the air in there heats up, uh, to even just to match room temperature compared to what's in the fridge, it'll expand, and that's the same thing. It's that those little gas molecules hitting the side, and the more speed they have, the harder they hit the side, and the more they push out. Okay, so there's 3 possible options that can occur in these collisions. We kind of almost skip this because I've already jumped to the next slide, but you could either have a loss of energy. Well, this is false. We don't have that. You could gain energy. This is also false. You can't gain energy in this situation. But the energy of these particles can remain constant before and after the collisions, and this is true. I don't really know why this slide is in here. I don't think it is needed. Okay, so we already did this one. Jump ahead. Okay, so not all particles at a given temperature have the same amount of energy. This is just kind of one of those rules that you kind of need to memorize. It can't explain it at grade 11 chemistry level, but basically this is kind of a curve of a graph of at a certain energy level or a certain temperature. You'll have some particles that are much lower energy and some particles that are much higher energy, and then the bulk of them are kind of in the middle here, middle low, I suppose. Uh, just because there's this spread, and it's because of how they bounce around in the container. And I'll show you guys something in class tomorrow, and you'll kind of see what I'm talking about. Where some of these really fast ones go, and then they hit one of these slower ones, and then it sends that slower one fast again, but it slows the fast one down. And so that's why you get this back and forth of, some are almost like stopped uh, because of just the way they collide with other particles. That's the gist of it, anyways. Whatever the case, they don't all have the same amount of energy at a given temperature. All right, temperature. So the average kinetic energy of the particles is indicated by the temperature of the matter. So that last graph we had, if we increase the temperature, you'll see that the average will increase as well. You'll still have some of those slower particles, but you'll have more faster ones to bring the average up as well. All right, so KMT for gases. So this is KMT is mainly for gases, to be honest, just because it's more interesting what gases do. 'Cause solids and liquids are kind of boring in how they interact with each other, really, for the most part. So gases super easily compressed. We already talked about that, and they have really low densities, right? So you can see, they're spaced out in this container, right? Easily compressed. So you guys, I don't know if any of you know how an engine works, but this is essentially how your engine in your car works. Um, you get gas and air, like gasoline, sprayed in as a tiny little droplets into the air that's coming in, goes into the intake like this, comes into the piston, and that's while the or cylinder, sorry. This is the piston right here. This is the cylinder walls on the outside. Uh, as that piston goes down, it sucks in this air and gas mixture, comes down, and then the crankshaft here goes around, comes and pushes that piston back up. Now, this little guy seals up so nothing can come out either the intake or the exhaust at this point, but it compresses that gas. And when it compresses that gas, uh, it creates more efficiency basically for your engine. You're going to get more bang for your buck. And then the little spark plug, which is right here, top dead center, um, explodes and that burns that gas and it drives that piston down. Bam. And drives the crankshaft down and creates rotational motion right here. That's this part. And that's what actually gives your wheels motion through a series of drive shafts and things like that. But that creates the spinning really, really fast. And I'm talking like thousands of RPM, revolutions per minute, that this actually runs. So then that comes back up and it pushes out that exhaust gas out the exhaust. And then it does the whole thing again. Once it gets to the top here, you go back to this stage where it pulls in the gas, compresses it, fires it, shoots it out. And this is a 4-stroke motor, meaning it has 4 strokes. 1, 2, 3, 4. And then it's a full cycle. Side note, really, but just showing that gases are easily compressed and you're doing it every day with your car when you drive it. So to do this, gas must particles of gas must be far apart and loosely packed. There's no other way we could compress it. If they were closer together, and if they were tightly packed, you wouldn't be able to compress it. They also have no definite volume and they diffuse really, really easily. So they will fill a container and those particles will diffuse throughout, like this example right here in the bottom. That's because intermolecular forces of attraction repulsion are very, very, very low. So these IMFs, super, super low, means that things can just move around really easily. There's no barriers, there's nothing slowing things down. All right, KMT for solids. So solids, not easily compressed, have high density, right? These particles are packed together really tightly. So they're very close together already, and they have more particles per volume than gas and liquid. Diffusion is really poor through solids, and this is, again, because there's no space between those particles for things to diffuse into. It's just too tight. Definite shape and volume of solids, and that's because, again, these particles are held together and don't move. So they have very, very strong intermolecular forces holding those together. So there's a couple different kinds of structures we can have. Either we can have crystalline and amorphous solids. So crystalline means that the particles are arranged in a geometric three-dimensional pattern. So crystals like diamond is the classic one. Diamonds are arranged in a very geometric three-dimensional pattern. I don't know. I don't think any of those are diamond. Hold on. Give me half a second here. Um, uh, what's a crystalline structure of diamond here? It could be this one actually. It looks kind of like that. It's kind of hard to. None of these show it very well. This is probably one of the better ones. Oh, what? Okay, sorry. Open a new tab. All right, so you've got graphite, which is in your pencils. Uh, you've got your diamond right here. I don't even know what BC8 is. Graphene, you may have heard of. Uh, it's gonna be one of the these nanotube, this nanotube and this. It's called the buckyball here. Are made out of graphene sheets. Graphene is the material of the future. It's the strongest material by far, and I'm talking like, oh, how many times more? It's like than steel. It's ridiculous by mass or by volume even. Once you layer these on top of each other, the forces are so strong between these carbon molecules, and you can roll them into tubes. You can make them into spheres. You can do all sorts of things. You can layer them and just create super, super strong structures. So graphene is uh, definitely going to be, you're going to see a lot of that in your future. So those are some examples of some crystalline structures. All of those are. They're arranged in a three-dimensional geometric pattern. Each element and compound has a unique crystal structure. So crystals can be held together by ionic attraction or by covalent IMFs, intermolecular forces. If you see IMF, you know that it's intermolecular forces. We don't really talk about intra in this in kinetic molecular theory because we're talking about forces between molecules. So if you see IMFs, it's inter. Uh, if I'm ever talking about intra, we'll say the whole word. So between NaCl, ionic attraction, this is a crystal structure where they alternate the positive Na and the negative Cls. And something like sugar, you have these intermolecular, the dotted lines holding the sugars together in these layers. So IMFs can be strong or weak, but are strongest in ionic solids. Hard to pull those apart. So another picture here. So amorphous, uh, Greek for without form. Whenever you see something with like a in front, it means the opposite. Like typical and atypical. Atypical means non-typical. So non-morphous, without form. Morphous means form. So it's an irregular arrangement of particles. Something like glass is amorphous. There's not a ton of things that are amorphous. As far as natural things, well, mm, can't. Well, like obsidian, but that's volcanic glass. So I mean, it's the same thing. I'll think about that. Think if I can come up some with some. You can probably look it up. What what natural are there any elements that are amorphous and see what you can find out as far as solids. I doubt there's very many. So candles, glass, rubber, plastic. There's some examples right there. But yeah, none of these are. Glass is the closest thing to being straight up elemental. And it's silicon. I can't remember exactly what glass is for formula. Okay, and then KMT for liquids, not easily compressed and have high density. So we count on this. We use this a lot in mechanics for any hydraulic system. We count on that not being compressed. And they have high density. So there's a lot of stuff packed in a small space here. Not as high as solids, not a high density as solids, but particles will still be close together and densely packed. But there is some motion there, which is why we can diffuse things through it more easily. So it does not have a definite shape. And IMFs must be weaker, allowing some movement. And that's because, again, we have more energy. It's warmer than the solid version, so those forces are they're fighting against those forces a little more because they've got more energy to do so. And they have a definite volume. IMF's strong enough to limit distance of particle movement. So it's kind of just in between the gases and the solids for that reason. Okay, so you should be able to use this kinetic molecular formula to explain these properties. We talked about the properties last lesson, you know, easily compressible, diffuses through, all those different ones. Well, now you kind of have a context of why that is. Talking about energy and talking about space between molecules, that's really what kinetic molecular formula is. And it really makes sense. So make sure you understand that concept so that you can apply it to all sorts of different questions. Okay. So you should also know what intermolecular forces are, elastic collisions, kinetic energy. Those are all great test questions. I'm almost guaranteed going to ask you, explain the difference between intermolecular and intramolecular forces. Um, I'm going to ask you about all these for sure. So make sure you know them, okay? And these are just terms that'll show up here as well. I may ask about crystalline and amorphous. What's the difference there? Stuff like that. So make sure you guys know this stuff. I know it's tough when it's theory. You're just going to have to memorize some stuff and and if you're not understanding the concepts, this is the time to get help and ask. Come in at lunch, send me a message, be like, "Hey, I don't understand this part. Had the bigger picture or whatever," and I'll try and help you help you understand so that it's not just straight memorization, that it actually makes sense. Okay? Good luck, guys, and we'll see you tomorrow.